This video is about one of the fundamental operations of vectors in Euclidean space, which is the so-called dot product of two vectors. So in this video, we will define and introduce some of the basic properties of the dot product with the aim of understanding one of its most important formulas. And this formula is important for several reasons, but one of which is that it allows us to think about what is the angle between two vectors in Euclidean space. And in particular, what does it mean for that angle to be 90 degrees, which is to say, what does it mean for two vectors to be orthogonal to each other? So using these ideas, we'll be able to state and prove a generalized version of Pythagoras' theorem. Okay, so given two vectors in Euclidean n space, the dot product is actually a very easy thing to calculate. It's a number which we compute just according to this formula here. So the dot of x with y is just x1 times y1 plus x2 times y2 all the way up to xn times yn. So just to give you a very simple example here, if we take two 3 vectors here, then the dot product will just be computed according to this formula. So we multiply all the components together in order, and then we add the result. And that's how we compute the dot product. Okay, now the dot product has it behaves very much like multiplication does. It has a few laws, and those laws are very similar to how multiplication would behave. So for instance, x times y is the same thing as y times x for numbers, and the same thing is true for the dot product. Dot of x with y is the same as the dot of y with x. Multiplication also distributes over addition. So x times y plus z is the same as x times y plus x times z, and the same sort of thing is true for the dot product. Okay, now let's get back to that formula that I mentioned earlier. So I want to explain why this formula in the blue box is true, but I'm going to have to take something for granted, and that is the fact in the red box. So that's this fact here. Now this fact is just a fact about triangles, and it's just saying that given a length A and a length B, and the angle that's between the two sides of this triangle, let's say theta, then we can compute the length of this side here, C, according to the formula here, which is called the law of cosines. So I suppose this is a formula from high school, so it's really not too much to take for granted. But it actually turns out to be really the underlying reason for why this fact here is true. And let's try to see why. So let's consider two vectors, x and y. So let's say this here is x and this here is y. Then the vector that points from x to y here is algebraically very simple. It's just y minus x. Okay. So from two vectors x and y, we can build a triangle, as we've done here. And we can consider the angle that would be between x and y here. Then using this law of cosines, if we think about the length of this vector x here, let's think about this as the side A, and think about this here as the side B, and think about this vector here as the side C, then using the law of cosines, we can express the length of this side length C just according to this formula here. So C squared is equal to A squared plus b squared minus 2 times the length of, or 2 times a times b times cos theta. Okay, so that's just according to the law of cosines, but we could also have expanded this length c in another way using the dot product, and that's just coming from this formula up here. So we know that the length of a vector squared is just the dot of the vector with itself, and you can actually very easily see that from the formula for the dot product. So in that case, we can expand this here. So here we'll just get that y minus x dot y minus x is equal to the magnitude of this vector squared. And then I said earlier that the dot product behaves much like multiplication. So that's a helpful way to think about what's going to happen next, because how do we multiply two brackets? Well, we consider this cross term. So here we would get y dot y. And then we would have two cross terms that are similar. So we would have y dot x And then we'd have, so negative y dot x minus x dot y. But then using this law here, sorry, this is wrong on this side here. This should actually just be y dot x. And in any case, the end result is that we can group those two terms together and we get 2x dot y. Okay. Then multiplying or taking the dot of x, negative x with x, we will just get here positive x dot x. Okay, good. So having this, then we can see that this term here actually just becomes the absolute value, well, the length of y squared, and then the length of x squared. And now you see the reason for doing it this way, because there's going to be some cancellation. Since everything is equal, we must have that these two expressions are equal. And now we can cancel off the x squared with this x squared up here, and the y squared up here with this y squared up here. And what are we left with? Well, we're left with negative 2 absolute value x, absolute value y, cos theta is equal to negative 2x dot y. And now we can just cancel off the 2's here and get the formula that we're looking for, which is up here. Okay, so that gives you an explanation for why this formula is true. And it also gives us a very good way to interpret what does it mean, well, to define what does it mean for two vectors to be perpendicular to each other. Because if theta was equal to 90 degrees, if this was a 90-degree angle here between x and y, then cos theta would be 0, and so the dot product would be 0. So this suggests to us a general definition, which is the definition that we take for perpendicularity of vectors, and that's just given here. So we say that a vector is x is perpendicular to a vector y, just simply if the dot product of these two vectors is equal to 0. And then we can just prove a very, very, very simple fact, and that is that if we have two vectors, so you can actually consider this as a generalization of Pythagoras' theorem, but if we have two vectors, let's say x and y, and x is perpendicular to y, then, okay, let's just consider the triangle that's formed by these two vectors, right? So we have here x, then we have y, which is perpendicular to x, so it would look something like this. Not yet perpendicular, let's try again. Okay, here we are. Not yet, but you get the idea. So this is perpendicular. And the vector pointing from here to here, the hypotenuse, is just going to be the sum, just because that's how you define vector addition. And so you can ask, what is the magnitude of x plus y? What is the magnitude of the hypotenuse squared? And then we can again use this law that we saw earlier. I can express the magnitude of a vector squared in terms of the dot product, just like this. And here we can use again our cross multiplication story, multiplying brackets like this. And what do we get here? We're just going to get x dot x plus 2x dot y plus y dot y. And this is just equal to, well, we know it's equal to x squared, just again by what we said. And then the whole point of the perpendicularity assumption is just that this is going to fall away. The x dot y here will be 0, and so that will allow us to just make that term fall away, and so we're just left with the formula that we're interested in, which is this one here. And so we've just proved this formula. Okay, so that's it for this video. We're going to be using this concept of perpendicular vectors very much in what follows, which will involve what's called orthogonal matrices. Okay, thanks.